Hey, what's up?
So we just want to get back to you. I think you emailed me back.
Yeah.
About the arm wrestling.
Yeah.
Yeah. We want to get back to you about that, and we also wanted to check and get recruit this guy and recruit as well.
How many did you guys? So within before 5. Okay, yeah, that's fine. So there's gonna be a couple groups of 5 because there's I think 42 students in the class. Okay. So one other group actually already reached out to me. So they're a group of 5, and you guys will be the second group of 5.
Okay. Awesome. Yeah. Cool. Cool. Yeah. And then the arm wrestling. So I was gonna send an email, but I was like, you know what? I'll just explain.
Sure. Yeah.
So Marshall has a little. He's the founder of ideas.
Okay.
I've seen a couple of different analysis on arm wrestling.
Okay.
And we were thinking of doing so depending on how close your elbow is to your shoulder, the shoulder point, it's how long your bicep muscle is, and it also changes the angle between arm and your bicep. Okay. So that's the the parameters we're going to change. Okay. And also the injuries when we're talking about your shoulder injuries, also bicep muscle abscesses. I saw when I was talking about it. Mm-hmm. So were those the 5? I know you're talking about 5 different analysis on it. Yeah. So you're talking about 5 different arm positions, or?
Yeah. So I'll give you an example. So last year, someone did a group did basketball, and so they did 5 different actions in basketball: shooting a basketball, getting a defensive stance, rebounding a basketball. And so those are 5. So with arm wrestling, it's a lot more constrained, I guess, what you're doing. Yeah. But it sounds like you guys are approaching it from the right way. Yeah. And so I guess what I would be interested in is, different arm positions and how the amount of torque you can generate depends on how long your arm is and things like that.
How about,
I think that'd be interesting.
Yeah. How about we try to determine the different arm positions, do our research this week, and get back to you on Thursday. Okay. See if you like it better.
Sure. Yeah, I think that'd be. I'd be interested to see if there's certain positions that actually put you at higher risk of injury.
There is.
Okay. Yeah. I think if you try to approach it in this way, I think it sounds like there's enough to go on there. I would like to see maybe if you email me on Thursday just to let me know, but it's sounding like it's sounding promising. Mm-hmm. So I think kind of when you first floated the idea, it's like arm wrestling. But I don't know anything about arm wrestling. So I said that's why I got back to you. I said, I want to learn more about your guys' plan a bit more before I say yes or no. So, but yeah, it's sounding good. But you can email me Thursday just so I can give it a full look over it. Yeah, it's sounding good. So yeah.
Cool. Awesome. Thank you.
Yeah. Mm-hmm.
I was going to show you something on the computer, but it's not coming up. I was trying to approach this FEA problem in class, but I need formula. So I'm doing different analyses on the which came up. I saved them on USB drive, but it seems to be corrupted. Okay. But I was just wondering if maybe I was going to talk to you after class, but maybe after FEA. I don't know if you're going to stick around.
I have a meeting at 7 today, but I do have a little bit of time after FEA. Okay. If you want to, if there's screenshots and stuff, you want to email it to me, then I can maybe take it.
Okay. I'll just.
And then maybe you can email me the images, and then maybe we can go back to my office right after FEA.
Okay. So that's going to be at 6:47ish.
Yeah, 6:45, 6:47.
Okay. Yeah. Okay. Cool. I'll just come back here.
Okay.
Thanks so much.
Yeah. All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. Week 11. We're in November now, and so now starts the countdown towards Thanksgiving. So we have 3 weeks of instruction until then. So we have this week, next week, and then the week after that, and then after that we have Thanksgiving, which is never can come soon enough. And so just a little bit of a preview about where we're going to go over the next couple of weeks. So we are going to have one midterm exam before Thanksgiving. It's actually going to be the last class session before we go on Thanksgiving break. So that's going to be November 17th. And so it's going to be 3 weeks from Thursday, basically, okay? Or 2 weeks. 2 weeks from Thursday. Yeah, 2 weeks from Thursday. Okay. And so you guys can look forward to that. Just like I did for the first midterm exam, I'm going to put out a study guide. I'm going to do a review video and so on and so forth. You know, the top, I'd say the content on the second midterm will probably be a little bit more difficult than the first one. And I'm trying to see how I'm gonna do the exam, because these problems are, you'll see today, the problems that you do are a little bit more time consuming. And so, you know, I need to kind of give it some good thought about how I want to do it. But, you know, that's kind of the plan. So what I'm hoping to do is to kind of finish all the dynamic stuff kind of before that last week, and then, you know, and then we can go on from there. Okay. All right, and so the plan for today is, you know, we still have a bit to go on human motion kinematics, and so I'm going to go ahead and finish that topic up today. We're going to do an example, and then you know, we'll go from there. All right, are there any questions I can answer before we get started for today? All right, so remember, homework 5 is out there too. So homework 5 is largely going to be based on this stuff. And so actually the example problem that I'm going to do today is actually from the homework, but it's the challenge problem on the homework. And so it's an optional problem for you to do on the homework. We're not going to do all of it together in class, but I do want to kind of show you it just so that you have an idea of how to kind of approach these types of problems. Okay, all right, so let's go and get started. And so what we left off on was human motion kinematics. All right, so this whole unit is all about, you know, what are the kind of the state-of-the-art ways that can we track the kinematics of human motion. Okay? So remember, what I mean by kinematics is basically the terminology and the concepts that we can use to describe the motion. Okay? Oh, sure. Because when you think about describing motion, yeah, there's lots of ways you can describe motion. So if you see like a ballet dancer, it's like, oh, that's beautiful. Or you see like a football player, you know, running over people, like, wow, that's intense, that's savage. But you know, when I say describe, what I mean is quantitatively. And so describe it in terms of numbers, in terms of, you know, describe it in a systematic way that we can actually perform computations on. And so, because ultimately what our goal is, you know, we want to be able to compute, you know, what are the muscle forces, what are the joint reaction forces that are needed to produce motion. Okay, so very similar to the way that we did in human statics. It's just that with motion, it kind of becomes a lot more complicated. Okay, and so we have to spend a bit of time talking about, you know, how can we describe the motion in a way that that is practical and kind of feasible. Okay, and so the way, you know, what I'm kind of teaching you is I would say a quite modern approach to tracking motion, as it relies on motion capture. Okay. And so we spent a bit of time talking about motion capture last week. But the way motion capture works is that you wear these specific suits, and these suits have these motion tracking markers on it, and the positions of those markers are tracked with cameras. Okay, so it looks kind of goofy when you do it, but then what you get is this kind of very rich amount of data. Okay, and so what we're learning is basically how do we go from motion capture data to actual kinematics. Okay. And primarily, you know, what we're mostly interested in terms of kinematics are the joint angles. Because if what we say is that if we can track the joint angles, we can compute them, you know, and track those joint angles as a function of time, we can use those joint angles in a dynamics analysis, which we'll see probably starting on Thursday. Okay. Right. And so that's kind of where we were. And so we kind of stopped in the middle of a derivation. So I'm actually going to go back to the previous notes just to kind of remind you, because it was kind of a lot to write down, and I'm pretty sure most people wrote it down from last time. And so I'm just going to pop back in there just to let you know where we were, and then we'll kind of pick up the derivation from there. Okay. All right, but that's just kind of a recap in terms of what our goals are in this particular section. And so are there any questions on this? Okay, all right, so let me go ahead and hop back to the previous week's notes. Okay, and if you remember, we were working with this kind of airplane analogy. And so what we're saying is that if you're sitting in an airplane, the airplane has to undergo a series of maneuvers in order for it to get into the air and for it to kind of point in the right direction. Okay? And one way that we can kind of characterize those maneuvers is through a series of rotations. Okay? And so if we draw a coordinate axis that kind of lines up with the plane, so we draw kind of one axis going down the nose of the plane, one going down the wing, and then one that's kind of pointed straight down towards the ground. We can characterize three rotations along those axes to characterize the ending position of the plane, or I should say the ending orientation of the plane. Okay? And so the three angles given are theta, phi, and psi. Okay? And those correspond to rotations about the z-axis, the y-axis, and the x-axis. Okay? And what we did from there was that, given these angles, we form these transformation matrices. Okay? And so remember, these transformation matrices, the point of them is to give us a kind of a mathematical way to transform between one kind of axis orientation to another, okay? And we did kind of a fairly lengthy derivation in 2D of, how we can derive these quantities. And we're kind of now in the middle of a 3D derivation, okay? But what we did in 3D was we said that, okay, we're going to perform these three rotations. If we kind of consider each of them individually, each individual rotation is basically a 2D rotation. So we basically took our 2D transformation matrix and kind of put them in different positions in the 3D one, okay? And we formed these three transformation matrices here, okay? So we have our lab R1, and so that's the transformation from kind of a stationary coordinate system, kind of like a classical X and Y, to the first orientation, okay? And then we have R12, okay, R1, R2, and that's the transformation from the first orientation to the second one. And so that's after, let's say that we tilt it upwards. And then we have 2R3, which is the transformation from the second orientation to the third, okay? And so if we were to limit our rotations to just kind of one plane at a time, and so if we were to do just kind of 2D rotations, one after another, our transformation matrices would look like this, okay? Right, and so even if we're in 3D space, if we were just to rotate along one plane, then we can just use one of these three transformation matrices. Okay, and so that information is useful if we're just doing a single rotation. But for any kind of generic three-dimensional orientation, that usually involves rotations in all three dimensions. Okay. And so basically what we're going to need to do is we need to combine these three transformation matrices to get kind of one transformation matrix, kind of a general transformation matrix for a generic 3D rotation, okay? right? And so that's what we seek. And so we basically seek just one transformation matrix that covers kind of all three rotations at the same time, okay? And luckily, you know, the answer to this is actually going to be quite simple, or it's simpler than I'm making it sound like. Okay? Because the idea is that, you know, for any generic 3D orientation, you can obtain any 3D orientation just by performing rotations in those three planes. Okay? And so the idea is that you only need to do 3 rotations to get any 3D orientation that you need to. Okay? And those three rotations are given by these 3 angles. Okay? I know we define these angles relative to a plane, but we can kind of make them generic and describe anything else. Okay, so that's our goal. And so basically our one transformation matrix should cover, you know, basically these 3 rotations. And so our one transformation matrix should have all 3 angles that we have here. Okay. All right, any questions on this? Okay. All right, so actually let me hop back just to kind of save space. Okay. And so let me call this combining transformation matrices. Okay. And so the transformation matrices have this nice property. If you're going to do successive rotations from one after another, what you can do is all you have to do is you just have to multiply the individual transformation matrices to get kind of a bigger one. Okay? Okay. And that's really all it takes. And so, you know, all the transformation matrices are square matrices. And so we can multiply them by each other to get kind of a square matrix. Okay. And so for an example, you know, let's go back to our plane. Okay. And so if you remember, the first 2 maneuvers that we did with our plane was we turn the plane. And so we did a rotation in the z-axis. Okay. And if you remember kind of the physical situation, this is when the plane was on the runway. You kind of had to make a turn in order to get onto the runway. And the transformation matrix that we used to describe this was this one, right? And so after the plane had kind of turned its nose, you know, when it's taxiing, we call that configuration 1. And so to go from the lab, kind of the lab frame, the fixed frame to configuration 1, we had lab R1. Okay. Okay. And so after we got into the runway, you know, the plane starts to take off. The next kind of change in orientation that the plane underwent was that it tilted upwards. And so the plane basically starts to take off. Okay. And that was a rotation along the y-axis. And so remember the transformation matrix that we used to describe this was 1R2. Okay, so what that's saying is that we started in configuration 1, we rotated, and then we're going to end up in configuration 2. Okay? So we can combine these. And so, you know, instead of having 2 transformation matrices to kind of describe this process, we can describe it with just one. Okay? And so if we take lab R1 and then multiply it by 1, R2, okay, what we get from this is a single transformation matrix. Remember, this is 3 by 3. This is also 3 by 3. Okay. So we multiply these together, and what we get is lab R2. Okay. So this is a single transformation matrix that'll take us from the stationary coordinates, the kind of the starting XYZ positions, and then get us into orientation 2. Okay. Okay. So basically both rotations are going to be encapsulated into that single matrix. Okay. And so, of course, you know, the key to this is that when you multiply transformation matrices, kind of the inner dimensions have to agree. Okay? And so if you kind of look at this, for the first matrix that we are multiplying, the one we have orientation 1 kind of in one state, and then for the other one we have orientation 1 as the kind of beginner state. So these two have to match up in order to perform a transformation matrix combination. Okay. Because the idea is that you're doing one kind of rotation after another, or one one configuration change from the other. Okay. All right. Any questions on this? Okay. And so we can continue this. And so, you know, this is one transformation that goes from the lab coordinates to orientation 2. But we had a third configuration here, which is after we did a rotation along the x-axis. Okay, so this was kind of maneuver 3. Okay. And remember, the plane did this to turn in midair. And so the transformation matrix that we defined for this, like that, okay? And so we basically started in configuration 2, and then we performed our rotation, and that got us into configuration 3, okay? We can do the exact same thing with this, and so we can combine it together with the previous result. So we take our previous result, which is lab R2, and then we're going to multiply this by 2R3. Okay? So once again, we see that the inner dimensions here, they are matching. Okay, so they're, you know, one starts at configuration 2, the other one ends up with it. Okay. And so, you know, what you can kind of say is that those kind of middle dimensions will cancel out. And we end up with lab R3. Okay. And so that transformation matrix has all 3 rotations kind of built into it. Okay. And so that's kind of the single transformation matrix to say that, you know, if we start with just a position in our stationary coordinates and we wanted to rotate to the planes coordinates, we would just multiply by that transformation matrix. Okay. So of course, we can actually do the algebra for that transformation, because you basically have three 3x3 matrices multiplied by each other, all with sine and cosine at different angles. And so it's not a pretty calculation, but it's technically doable if you have 45 minutes to spare for some reason. Okay, but I already did that for you, or rather, the textbook did it for you. And so we can write kind of the answer. And this result here is actually important for motion capture as well. Okay. And so what I'm going to write down is basically the generic 3D transformation matrix that has rotations in all three directions. Okay. Okay, so the value of map R3 is the following. So it's a 3x3 matrix. And it has the following results. I'm gonna draw lines just to kind of just so you can see kind of the different rows and columns, because some of the terms here are quite long. Okay. Let me write it all down, and then I'll zoom out just so you can see it all, because it's kind of a lot. It's taking like my entire concentration right now just to make sure I get all the terms right. Okay. So that's the full 3D transformation. Okay. And so if you have basically two different orientations in 3D, and they can be obtained by rotating in all three dimensions, then this is kind of the transformation matrix between them. And so, while you're writing that down, I will say the good news is that I'm not going to make you, plug in for this, because it's a little bit cruel. It's a little bit cruel that I'm making you write this down right now in your notes. But I will kind of show you how this is used in practice, because basically the way this is used in practice is that we use computers to basically compute these transformation matrices, and then from those transformation matrices we can relate it to this this result here to compute the actual angles. Okay? Remember, what we're after here is the angles. We're not actually going to be computing the matrices themselves, at least not in this way. We have another way that we can compute transformation matrices in a second, but then we can use those results to compute these angles. Any questions on this? All right, so let me go ahead and write that down. So this result is used okay. And so you'll see from the problem that we have other ways that we can use to compute transformation matrices, and then from those we can actually compute what the angles of rotation are. Okay? Because that's our goal. Because those angles of rotation, the theta angle, the phi angle, and the psi angle, those can be used to characterize the joint angles, kind of in generic in 3D. Okay. So let me go ahead and do, let's do the example now, just so that, we kind of take a break from all these sines and cosines. And then I'll show you kind of the other way that we can use to compute the transformation matrices. Okay. Okay. All right, so in this example, we have a 3D motion capture setup on the lower leg. So I'm gonna go ahead and draw the lower leg here. And we have seven mocap markers. So we have marker 1, marker 2, marker 3, marker 4, marker 5, marker 6, and marker 7. Okay. And the positions of those markers. And so let's say that this person is just standing still for now. So they're not moving. And so each of the markers, we can describe their X, Y, Z positions. Okay. Okay. And so marker 1, this position is going to be minus 4.14, minus 21.76, and 48.52. 2, its position is minus 5.48. And all of these are centimeters, by the way. Okay, so those are marker 2's positions. Marker 3 is minus 9.04, minus 23.03, 29.5. Marker 4, minus 2.97. So that's marker 5, marker 6, and then marker 7. Okay. So a lot of numbers there, but you know, this is a pretty typical setup. And so you know, usually you're going to have multiple markers like this, and this is all just for one body segment, right? So this is all just for the lower leg. And so another name for the lower leg is, you know, we sometimes call it the shank. Neighbors, right? All right. Okay. And so what we want to do in this problem is, well, the problem itself has several different parts. I'm going to go through maybe a few different parts of the problem with you. Okay. We'll do the first part for now, just because it's kind of relevant to kind of what we, you know, what we just went over, and then we'll kind of do the rest of the parts as they become relevant. Okay. All right. And so in the problem, what is given to us is that we know that markers 3, 4, and 5. And so let me go ahead and draw a triangle between those three. So markers 3, 4, and 5, this is going to define our tracking coordinate system or tracking reference frame. Remember, whenever you have a mocap setup, you need to have one set of markers that can be seen basically by the cameras at all times. Okay? We call that the tracking reference frame. Okay? Meanwhile, the other markers, so 1, 2, 6, and 7, this is going to define the anatomical reference frame. Okay. All right, so the first two parts of the problem. So part A, we want to compute the transformation matrix between the lab reference frame and the tracking reference frame. Okay. And so the tracking reference frame, I'll just shorten it as TCS. Okay. And so TCS stands for tracking coordinate system. And so in part A, what we're looking for is this, this transformation matrix. And so we're looking at from lab R TCS. Okay. That's our goal for part A. Okay. And one thing I should note is that all these marker coordinates that I have 1 through 7, these are the coordinates of the markers relative to the lab fixed reference frame. Okay. All right, so basically based on the mocap marker position, specifically markers 3, 4, and 5, first of all, we're going to define the axes for the tracking reference frame. and then relate its rotation or relate its orientation back to the lab reference frame. Okay. All right. Any questions on this so far? Okay. All right, so let's begin. And so, the transformation matrix that we seek is going to have the following form. And so it's going to be 3 by 3, but we don't know what the rotation angles are, right? And so all we have are just the mocap markers. And so we don't know what rotations we need to get to do in order to get into this position, okay? And so let me tell you kind of another way that you can compute a transformation matrix, okay? Especially relative to a fixed frame like this, okay? Okay. And this is useful. Okay. Right, so we're going to use kind of this alternative method where if you're transforming from a fixed reference frame to kind of a rotated reference frame, this method is pretty useful. Okay, and so if we can use this method to compute the transformation matrix, we can then relate it back to the formula that we just went over to compute what the rotation angles are. Okay, and so one way that you can do this is that you can write, remember the transformation matrix is 3 by 3. And so each column of the transformation matrix each column of the transformation matrix is going to be the coordinates of the unit vectors in the new frame relative to the old frame. Okay. So basically what this means is that, basically we're going to compute this transformation matrix column by column, okay? Where this first column, this is going to be the X, kind of like the X hat vector, or TCS. Okay. This column is going to be the Y hat vector in TCS. And this third column here, this is going to be the Z hat vector for the TCS. Okay. And so if we define our rotation matrix this way, it's actually going to be consistent with kind of the 3 rotation form that we did before. Okay, so this gives you the exact same result. And so this is really useful because these 3 quantities right here, the X hat vector, the Y hat vector, the Z hat vector, those are a lot easier to compute. And I'll show you how to compute those in a second. Okay? We can then relate those back to, to find the angles from the transformation. Okay? And so basically what we're going to do is we're going to first define the X, Y, and Z directions in the TCS, okay? Because every coordinate system has the directions for its X, Y, and Z coordinate axes, okay? We're going to define what those directions are, compute unit vectors in each of those directions, and we're going to put them in the matrix. And that's going to be our transformation matrix. And then from that transformation matrix, we can compute the angles, and I'll kind of show you how to do that. Okay. So it sounds like a lot, and before I started computing stuff, I wanted to make sure that I kind of let you know kind of where I'm going. So this is kind of the way that you are going to kind of approach these problems. Okay. And so the way these problems are going to go is I'm going to give you the marker positions. The one you're going to do on your own is actually only in 2D, so that'll be a lot easier. So I'm showing you the 3D version here. And then based on those marker positions, you're going to define the X direction, the Y direction, and the Z direction, compute their unit vectors, and then kind of stuff them into this matrix. Okay. Any questions on this? Okay. And so, that's a lot of talking, a lot of instruction. So let's just kind of get to it. Okay. And so let's go ahead and define the X, Y, Z directions for the TCS. Okay. So let's start with the X direction. And so in the problem, if you read the problem, what it says is that basically the X direction for the TCS is defined as a vector that goes from marker 4 to marker 3. So let me go back up to this this figure up here, okay? And so basically our X direction for a TCS is going to be along this direction here, okay? And so if we draw a vector that goes from marker 4 to marker 3, this is going to be our X direction for the TCS, okay? And so we need to basically find out what that direction is. Okay, and so to get a vector that points from marker 4 to marker 3, we need to do vector subtraction. So we're going to do marker 3, its position, minus vector 4, or marker 4. Okay? And so we're going to subtract the X component, the Y component, the Z component of each of these. Okay? And so that's going to be a minus 9.04 minus a negative 2.97. Okay? And we have minus 23.03 minus a negative 15.62. Then we have a 29.53 minus 25.89. Okay. And so we perform that subtraction. And so that gives us a vector that points from marker 4 to marker 3. Okay? And so if we perform this arithmetic, and so we just to kind of add up the values, we get minus 6.04, minus 7.41, and 3.64. Okay. Right, so that vector there defines the direction of our x-axis for the TCS. Okay, but we're not quite done yet because we need to normalize this. So remember, in order to stuff it into the rotation matrix, these have to be unit vectors, and so they have to have a length of 1. Okay. And so what I'm going to do is I'm going to compute the magnitude of this vector. So the magnitude of this vector is going to be 6.04 squared plus 7.41 squared plus 3.64 squared. Okay. And so that gives us a magnitude of 10.23. Okay. And so to get a unit vector, we're going to divide each entry by this length. Okay. And so if we do that, we get minus 0.593, negative 0.724, and 0.356. Okay. And so this becomes the first column of our transformation matrix. Any questions on this so far? Okay, all right, so that's the x-axis. Now let's work on the y-axis. And so for the y-axis, from the problem, so this is given to you, and so you don't have to decide this on your own. Right? And same thing with the x-axis. And so, I said the x-axis goes from marker 4 to marker 3. That's given to you in the problem. So you don't have to decide on your own which direction is the x, y, and z. Okay. And so for the y-axis, what the problem tells us is that it's perpendicular to the x-axis. It has to be, and whenever you have a coordinate x, y, z system, the x, the y, and the z coordinates, they all have to be perpendicular to each other. Okay? And so it's perpendicular to the x-axis and perpendicular to the vector that points from marker 4 to marker 5. Okay. And so our y-axis is going to be perpendicular to both of those things. Okay. All right, and so there's a couple things we need to do here. So the first thing we need is we need to know what the vector looks like that goes from 4 to 5, okay? Because we have the x-axis. The x-axis is given to us, in purple up there. And so first we need the vector that goes from 4 to 5. Okay? And so to get that, we're going to do vector 5, or marker 5, excuse me, minus vector 4, or marker 4. Okay. And so we're just going to subtract its coordinates. And so we're going to have it minus 9.66 minus a negative 2.97 and minus 20.68 minus a negative 15.62 15.97 minus 25. So we perform the arithmetic, and what we get is minus 6.67, minus 6.69, minus 5.06, and 5.92. Okay. So that's our vector that goes from 4 to 5. Okay. And so our y-axis is going to be perpendicular to this and the x-axis. Okay. And so the best way to find a vector that's perpendicular to two other vectors is to use a cross product. Okay. All right, so our cross product, we're basically going to do. So this is the way I learned cross products, and so I know there's a formula form for it, but the formula is kind of way too long for me to memorize. And so what I do is I take this kind of imaginary matrix here, and then I just take the determinant of that matrix. Okay. All right, and so for the top row in the matrix, we have I, J, K, and so those are kind of the X, Y, and Z unit vectors in the stationary coordinates. Okay. And then each of the rows from here are going to be the two vectors that we want to be perpendicular to. Okay. And so for the first row, or the second row, excuse me, I'm going to write out the coordinates for the x-axis. So that's minus 0.593, 0.724, minus, and then 0.356. Okay. And then the other vector we want to be perpendicular to is the one that we just computed, which is the vector that points from 4 to 5. And so this can be a minus 6.69, 5.06, minus 5.92. Okay. Okay, and so we're going to take the determinant of this, and so that's going to give us the cross product. But of course, if you have a different way to compute cross product, I know there's other ways to do it too. Then just do it the way that you feel most comfortable. Okay. All right, and so I'm going to go ahead and skip the details here, just because I want to make sure I get through this example, before today ends. Okay, and so if you evaluate that cross product, what you get is the vector that looks like this, 6.09 minus 5.89 and minus 1.84, okay? And so again, we need to normalize this. So if we normalize it, we take its, just like we did before, we're going to find the magnitude of this vector, divide each entry by that magnitude. And what we get is 0.702 minus 0.679 minus 0.212. Okay. And so this unit vector here will become the y-axis of our transformation matrix. Okay. So this becomes second column. All right, any questions on that?
I have a question. Hello?
Yep.
What does normalizing entail? I didn't catch that part.
So normalizing just means that we're making its length equal to 1. And so if we take the magnitude of this vector right here, then the magnitude will be something that's not 1. And so in order for us to plug this into the transformation matrix, the magnitude has to be 1.
Okay.
And so we take the magnitude. So I think I fully showed it up here. Right. And so we have this vector right here. We compute
I see. You divided it. Okay.
Exactly right. And so the minus 5.93 here will be basically minus 6.04 divided by 10.23. And then we have minus 7.41 divided by 10.23. And then 3.64 divided by 10.23. Yeah. And so that's what gets us.
Thank you.
Yep. Mm-hmm. Right, any other questions on this? Okay, so that's 2 out of the 3 axes down, and so we just have the third one now, and so the z-axis. Okay. Luckily, by the time you get to the third axis, it becomes a lot easier, and so the z-axis here has to be perpendicular to both the x and y axis. Okay. Okay. All right, so I'm gonna set up a cross product just like before. Okay. So we're gonna take the cross product I, J, K. We're gonna plug in the values. The good thing about this is that because the x and y axes have already been normalized, we don't have to normalize this resultant. So we just have to compute it. Okay. And so the second row in that matrix, the second row of the first one of non-zeros, that's our x-axis. And then the last row in the matrix, that is our y-axis. Okay. All right, and so if we evaluate this cross product here, okay. And in the interest of time, I'll go ahead and skip that. Okay. And so what we get from this is 0.395. 0.124 and 0.911. Okay. So this here becomes the third column of our transformation matrix. And now we're ready to kind of put it all together, okay? Because we have the first column that was our x-axis, our second column is the y-axis, and the third column here is the z-axis. Okay, so let's go ahead and put it all together. And so what we have is lab R, yes, okay. And so our transformation matrix looks like that. Okay? And so basically to rotate from the fixed lab reference frame to the reference frame of the tracking coordinate system, we would have to multiply by this matrix here. Okay? All right, any questions on this? Right, and so, it's a doozy. And so it's a lot of calculations, but, hopefully it goes faster on your own when you don't have to narrate it to a class of 40 people. And so it's a lot of, I would say, tedious calculations, but none of it is super hard. You just kind of have to be systematic about it. Okay. Okay, and so let's take this result, because this result by itself isn't, it's cool, but it's not super useful yet. Okay, because what we want to learn is, from this, based on this transformation matrix, what are the rotation angles that we would need to do to go from the lab frame to the TCS. Okay? Because we have the mathematical relationship here, but it's also useful to know what those angles are. Okay, we're still not quite there yet in terms of determining the joint angles, because this is not between two adjacent segments. Okay, this is just the transformation matrix from the lab reference frame to just one TCS. Okay, but it's still useful to know that if we do have this transformation matrix, how do we actually go about determining what the angles are? And so to do this, we're going to relate it back to formula with the angles. Okay. And so actually, let me try one thing. And so the formula for the angles is this one right here. So actually, let me try to lasso this guy. I've never done this before, and so I'm doing it live for the first time. Okay. And so let's go ahead and bring this all the way down. Whoa. What the? Ah. It's working better than I thought. It's taking me a long ass time. I can just copy and paste. Yeah, that's probably a better idea. We're almost there. All right. There we go. Okay. And so we have this 3x3 transformation matrix, but we know that kind of based on, based on the way that we, computed it, it's going to be equal to this, to these expressions here. Okay. And so what that means is that each of the entries here, we can relate it in an equation to each of the entries, elsewhere. Okay? And so in particular, the easiest one to determine here is going to be to solve for the angle phi. Okay. Because if we look at these two entries here, so if we look at the very bottom left entry of the transformation matrix and the very bottom left entry of its formula form, then what we can see basically is that minus sine phi has to equal to 0.356. Okay? And unfortunately, I don't have the exact numbers for this because this is not part of the homework problem, but I wanted to show you how to do it anyway. And so phi here is going to be minus, or as I should say, inverse sine of minus 0.356. Okay. And so to compute the angles, you just kind of have to, in a clever way, kind of relate the entries of your transformation matrix to this one here, okay? So I'll do another example. And so now that you know phi, now that you know phi, we can basically, let me use blue. Okay. We can take this entry and this one right here, okay? And so based on those two, we can say that minus 0.724 is equal to cosine of phi sine of theta, okay? And so if we divide both sides by cosine phi and take the inverse sine of that, we can say that theta is equal to sine inverse of minus 0.724 divided by cosine of phi, okay? And you know what phi is because you just computed it in red just above there, okay? All right, and then finally, let's do green. All right. And so based on your knowledge of phi and theta, we can use that to compute psi. Okay? And so the nice thing about this is that, you know, there are some entries, quite a few entries on the first column and the last row where you don't have to deal with kind of a monstrosity of a term kind of up there. Okay? And so we use this information. We can say that minus 0.212 has to be equal to sine of psi and cosine of phi, okay? And so if we solve this for psi, we can say that psi is equal to sine inverse of minus 0.212 divided by cosine of phi. Okay. And so based on these, and so you don't have to use these three equations. I just picked them just because they were the easiest ones to do. But you can choose another three terms as well. But usually it's a good idea to start in the bottom left because that's the only one with a single angle in it. Okay. And so you can basically take any transformation matrix, compute what the angles phi, theta, and psi are. Okay. All right. Any questions on this? Okay. All right. So one last thing I want to go over, before we go, is to talk about inverse of transformation matrices. Okay. And so the transformation matrices that we have defined so far, have an old coordinate system and a new one. Okay. So remember, every transformation matrix that we define has kind of two markers associated with it. So there's one in the top left, and so that defines kind of the system that we're transforming to, and then on the bottom right, that's the system that we're transforming from. Okay. Okay. And so it's basically a one-way street. And so we're basically going to go from whatever system is on the bottom, and then we multiply that by vector, and then we get the corresponding coordinates in the system that we're going to. Okay. So it's a one-way street. But what if you wanted to transform the other way? So if you wanted to transform, in this case, we're going from B to A. What if we wanted to go from A to B? Okay. And so you might think that, this should have some relationship to this transformation matrix here. And so, we shouldn't have to go through that entire process from the example from before. Okay.
Sorry. I guess just to clarify, so is this notation different from what we were using before? Because before, like, lab was in the top left where A is, and we were going to the TCS.
It was this is always the same. I think I might have just used bad language here, but this lab RTCS, this is the transformation matrix to go from the TCS to the lab one. And so what I mean by that is if we have a vector here, this vector here defines a coordinate in the TCS, and so it defines some point P in the TCS, and we wanted to find its respective coordinates in the lab coordinate system, then we would multiply by this one. Yeah, so I think I might have mixed up the language when I was going through the lecture today. So I apologize for that. But that's the main convention. So this is in the bottom one where this is the one we're transforming from, and the top, that's the one we're transforming to.
Got it.
Mm-hmm. And so if you want to kind of reverse this, all you have to do is just take an inverse of the matrix. Okay? And so if we wanted to find B, RA, okay, this would be the same thing as A, RB inverse, okay? All right, and so on Thursday, when we wrap this up, there's just a little bit more in this section, I promise. And so we're going to use this property a lot, because what we'll see is that, practically speaking, based on the motion capture markers, there are certain transformation matrices that are easier to compute than others. Namely ones that are based on the lab coordinate system. But then when you actually go to use that in calculations, sometimes you need the inverse way as well. Okay, and so we're going to take some inverses, but just know that we have this relationship here. Okay. All right, so that's all I had planned for today. And so, I apologize, but for kind of mixing up the convention throughout today. But this is the one that we're going to use kind of moving forward. Okay. So thank you guys for coming out today. On Thursday, we'll finish this up, and you'll kind of see how this all. Hopefully, you'll see how it all kind of fits together. We'll kind of finish up this example in the meantime, and then we'll go from there. And so, hope you guys enjoy the rest of your evening, and I will see you all on Thursday.
What are you doing, Marsh?
Yep.
I think it was mentioned a couple weeks back, but you will be teaching 442 next semester.
I plan to. The department chair hasn't
Giving you.
He hasn't talked to me. Usually he comes out to talk to us, when we are giving our preferences for the next semester. He just hasn't gotten around to do that. But I do want to teach it, and I know that our department struggles to put enough tech electives out there, and so I don't see a reason why he wouldn't.
Do you know course?
Yeah, it's basically this course. It's kind of the same idea of this course, so it's biomechanics, but we focus on blood flow. And so how can we apply fluid mechanics, like 333 stuff, to study cardiovascular disease and high design medical devices?
Oh, so it goes into devices as well.
A little bit. I mean, we focus more on the simulation technology, and then the devices would be some of the applications for that simulation.
What kind of programs are used to simulate?
So you can use ANSYS. So ANSYS is actually quite popular, but the one we're going to use in the class, mostly because it's free, is called SimVascular. And so it's an open source. It's designed for research software. It's designed for research use, but we use it in the classroom to kind of illustrate a lot of the ideas. So it's totally free. And the nice thing about it is that there's no limit, element limit. So you can mesh it to whatever your computation.
In the past, what times were the classes offered?
It's always kind of around this small actually. So around like 4 to 5:30, 5:30 to 7. Yeah, it's always in the evening because it's a tech collection. So you know, grad students have to be able to take it, and a lot of our grad students they work during the day. So
okay.
Yeah, I'll keep. I know a lot of people have been asking about it, so I'll keep you guys updated. So once I get news from the department chair about if it's going to be offered or not and what time, then I'll let you guys know.
Okay. The reason I ask is because my senior design project is with Edwards Life Science, so I feel I could gain a lot learning from that class.
Yeah. No, definitely. Yeah, and every year there's always at least one Edwards group, and I always have some of those students.
There's 2 this year.
Oh, awesome.
Yeah,
awesome.
and I'm in one of them. The project I'm in surrounds the mitral valve.
Okay.
Is that something in the class as well?
Yeah, definitely. I mean, we talk about the valves. The valves are actually pretty difficult to simulate, but then we'll talk about its biomechanics and we'll talk about its properties and how it interacts with blood and all that stuff too. So
I assume on the native valve rather than some replacement.
we talk a bit about replacement valves, but yes, mostly on the native valves.
Okay. Well, hopefully you'll be offered.
Yeah. I'll let you guys know.
Thank you.
Yep.
That's since 6:45, right?
We can talk right now briefly if you want.
Oh, I don't have it set up.
Okay.
Because I didn't know that you have to pull the file in with it.
Okay.
The folder, I guess.
Okay.
And when I try to open it, it's saying it's not finding the folder.
Okay. Yeah. Let's be at 6:45 then. So.
Okay, cool.
Yeah.
Awesome. This is gonna be quick because I just want to basically try and draw it on my hand. So it's like just the brake pedal.
Yeah.
And then it comes down. And then it's going to pivot around this.
Okay.
And then the master cylinder is going to be attached right here.
Okay.
So that when you go push it this way,
yeah,
there's going to be equal reaction force. It's going to come that way and compress the master cylinders.
Okay.
So I wanted to fix it around this.
Okay.
So that this moment, it combats it with an equal moment the other way.
I see.
And then it kind of does like a 3-point bend.
Okay. Right.
That's what I was trying to set up. Yeah.
Okay.
And some of the guys from FA were helping me, but we were setting up like fixed points, and it was kind of like shearing around the.
Yeah, so I think you're gonna have to set a bearing support there, so it could still actually rotate around.
Yeah,
if you fix that cylinder, that's basically the same thing as that, or you're fixing where the screw is or the hinge.
Yeah.
Whatever, then it's basically saying that that's a weld, basically.
Okay.
So when you push up here, it's just gonna shear around.
Yeah.
And none of it's gonna get transferred.
Yeah.
And so there you have to do a different support. I think it's called a bearing support.
Okay.
I haven't done it in a long time. But we can take a quick.
Okay, cool.
Yeah, but that's basically kind of what you have.
Yeah, I actually had it open, but I closed it. I didn't think I have time. That's fine. I'll come back later then.
Okay, sounds good.
Awesome. Thank you.
Yeah. Austin, did you have any final questions? Okay, all right. So I'll see you. Well, I'll see you in the next week.